We're gonna keep going. Do you remember this from yesterday? Did you lose sleep over it? Did you try a few? All right. I drew a blank yesterday. I have math professors in the middle of the lecture. We do this full board, full blown example, and my math professor was just like, I can't do it, guys. I don't know how to keep going. So he just walked out of the room, and we was just like, so do we leave? What's going on here? So it happens from time to time. I apologize for that. All right. We did our tree diagram. I want to say something about independent and dependent events, guys. Tree diagrams are your friend. Okay, you can basically anytime we're talking about two events, either they're dependent or independent, you can make tree diagrams, and it will solve almost every time. You'll be able to envision it and solve what you need to do. So if you can, it doesn't take that long to just make a basic tree diagram, especially if I don't ask for it, right? And so I encourage you to do that, and I'll try to do a couple. Anyway, so yesterday we talked about the sign, not putting up the sign, and you must concur with me that they depend on each other, right? Putting up a sign will determine what happens, right? So this is definitely dependent events, okay? So we did all of that. That was beautiful. We had it all figured out. It adds up to 1, we get 100%. And then it asked, B, what's the probability of someone falling? So we went and grabbed the 2 instances where someone actually falls, okay? By the way, I always tell you, right? It gets bad out here in the winter. Please take your time, okay? I don't want any dislocated anything, right? So make sure you pay attention. C is the one I got stuck on, right? I was kind of like, what? I didn't want to like figure it out in front of you because then you get confused, right? So now I kind of sat down, okay? So what's the probability? What's the probability of having placed the sign given that someone fell? If you are able to write that in using proper notation, that would be great. So kind of read it exactly the way it is. So it says this, probability of having placed the sign, so write this down, given that someone fell. This is what is being asked of you here. So now I'm going to scroll down. Okay. I actually want the tree somewhat on there, so I will try to. So now what's happening? What 2 events are we talking about? We're talking about slipping and falling. So watch what I'm going to do. You go probability of slipping and falling. And these are dependent events, correct? Okay. So remember that weird formula with the backslash? This has to be at the end, right? Slip slash. Okay. What comes in here? If you look at the formula, you're like, what formula, Mr. Dixon? This one. This one, right? These ones here, right? If you go A and B, like the 2 events, and you have the backslash, this one shows up first, right? Because that happens first. So we're going to kind of say that this is probability of falling. So now, what did I do? How did I come up with this, right? I determined that the question was asking for this, right? And then, so I started my formula the way it always starts. It's slipping and falling, right? The probability of both. But because they're dependent, this is the notation I've got to use. So I put this one at the end. Can I highlight this here? I'm just going to say that this is what tells me what I need to put there. Okay. And now let's go and get our numbers from the tree. We get it straight from the tree. Okay. I also added in my notes that this is the first, right, and this is the second event, so to speak, right? Okay, so what's the probability of slipping and falling when you go up to the tree there? Go up to the tree and find this one. I'm going to go up there, and it's the very first one. Slipping and falling is 0.1826. So I'm going to write this down, 0.1826. What's the probability of just falling? Or like, well, I just calculated it up there, right? It's these two combined. These two combined is your probability of falling, which I already calculated, and I'm just going to borrow that number. So that's 0.2846. Let's do pink here, right? I did probability of fall. I figured it out here, and it shows up here. Okay, probability of falling, and this one here, I put this in brackets, and I turned that into x. I don't want to keep rewriting that notation, right? And so now basically what you have is the equation partially filled in. You've got 2 out of the 3 things. What are we going to do now? We're going to divide both sides by 0.2846. I'm going to use a red pen for that, just because. Right, this cancels out. And x is equal to, if you divide these two, 0.6416, right? So x is 64.16%. That's the probability, right, of slipping, or of the sign being up given that someone fell, okay, because they're dependent. So that's that. This, can I just say that this, right, usually worth 2 marks. Okay, if that shows up, it's usually worth 2 marks, where you have to go and grab your numbers, and you have to set it up properly like this to know which numbers to grab, and then you figure out. Okay, I can guarantee you that a question like this, like the page 37, that something like that is going to be on the test. At least there's going to be one of these on there. I'm not going to even pretend to hide that fact. Okay. Okay. So now let's keep going here. I hope you tried some of these in the pages 40 to 43, had a couple of those. I want to talk about the bonus types questions that you saw today. So I'm going to skip a few here. Let's go to page 44. Page 44 looks like this. Events are independent if one of the following is true. So if you can show that left-hand side is equal to right-hand side, right? If you can show this, then the events are independent, meaning that one doesn't affect the other. Okay. Another way to know for sure is if I tell you a little story and you see that things are being replaced, like after being drawn, then it's independent. Okay. So keep that in mind. So let's do just a little practice question here. The probability of Mr. Erickson catching a walleye is 45%. I'm going to circle that. The probability of him catching a pike is 70%. The probability of him catching both is 35%. So you're given the probability of each individual catch, right? 45%, which is 0.45. Probability of pike is 70%. If I give you fractions, turn them into a decimal, right? Don't fear them. Probability of both, right? Catching both a walleye and a pike is 35%. 0.35. So let's check. Let's check if events are indeed independent. So we're going to go 0.35 is supposedly 0.45, the event, the one event times the other event, like that. And basically, if it's going to work out, if both sides are equal, you have yourselves an independent event or independent events. If not, it fails. Okay. So 0.35, you multiply these two, you get 0.315. Okay. And at this point, you can't just leave the equal sign there because you're lying. This is not a correct statement, right? So you have to do this. Okay. When you notice that they're not the same, cross off the equal sign. They're not the same. Therefore, events are not independent. They're probably dependent, right? Well, obviously, if they're not independent, then it must be that they are dependent, right? So if the walleye are biting, that's probably also going to mean that the pike are biting, right? Like there's a bit of a, like, they depend on each other. Like if one happens, the other one will be affected, okay? So I'm just going to have one example. The questions that I'm going to give you down the road will ask for this perhaps. So you need to be able to explain, right? Either if you notice something that's being replaced, or you can just mathematically check like this, okay? So this is a big page. It's supposed to stand out. So there you go. Let's keep going. I will take you straight to 47. Page 47. So I'm skipping a few pages. It says, find the probability, or a jar has 6 red, 3 green, 5 white, 7 yellow marbles. Find the probability that at least 1 green marble is chosen when picking 2 marbles with replacement. Okay, I'm going to highlight a lot of things here. Probability of at least 1. What should you be thinking there? Indirect reasoning. We're going to take the total, subtract the fact that there's one where there's no greens, right? If you want at least 1. The other one that I want to highlight is this. With replacement, what kind of events are we talking about? Dependent or independent? They're independent, yeah. Independent events. So this question is telling us a lot what needs to be done. But remember I told you about the tree diagrams? I love trees because I always go on trees. On tree stands when I go hunting, right? I sit on a tree and just wait for something to happen, right? So here we go. What we're going to focus on is what? We're focusing on the green, right? So let's say we draw the first marble. We're going to focus on green, not green. Correct? But Mr. Dirksen, there's like red ones and yellow and all that. No, we're just going to focus on it and not it, right? So how many greens are there? 3 out of? Oh, we need to figure out the out of. Can you please add them all up and make sure that there's 21? Is it 21? Okay, perfect. Thank you. So the probability of getting a green the first pick is 3 out of 21. Therefore, how many knots are there? Let's just use this, right? 21 minus 3 is 18. So we've got that. Then we're going to draw another one. Are we putting it back? Yes, right? So you still have 21 possibilities on that second draw. We're going to go green, not green, green, not green. So we're not going to focus on all the other colors, just green. because that's what we're focusing on. So we have 3 out of 21 there. Therefore, 18 out of 21 are not green. 3, 18. So you can just copy paste. This tree diagram screams independent events. It should, at least. Okay. Just put your ear really close to the paper and you'll hear it. Okay. Anyways, what we're going to focus on is probability of at least one green, right? What I'm going to focus on is 1 minus probability of no greens. Okay, that's what I'm going to focus on. And where's your probability of no green? It's right here. Probability of not green and not green is 18 over 21 times 18 over 21. It's not just 18 times 21, it happens both times, right? So allow me to use my calculator for this. So this is 324 over 441. Let's turn that into a decimal. This is 0.7347. And so, Mr. Dirksen, why is there 1 there? You always say 100%. It's the same thing. 1, 100%. I'd like to just deal with 1 and a decimal. So 1 minus 0.7347, right, is equal to 0.2653 or 26.53%. Let's highlight a few things here. Green. So, right, I'm just going to show you, right, that there's the probability of no green. I highlighted no green with green. It's kind of ironic, but anyways. So, right, because what's the other way of doing this? Of at least one green, right? At least one green, you could have added these probabilities here that you got from these branches, right? Because here you've got green, green. Here you've got green, not green. Here you've got not green, green, right? So these 3 branches, that would have been direct reasoning to add them up. But if it says at least one, take away the nots. Do indirect reasoning. That's how you get it, okay? True and false. Yeah, let's do that. Multiple choice. So if you this is to help you with Mr. Carrington's test, right? Or any test for multiple choice, right? Answering 2 multiple choice questions with 4 possible outcomes. What's the probability of getting both of them right? Let's just focus on this. And remember, tree diagrams are your friend. Okay. So the first question, you have the right answer and the wrong answer, right? It's right or wrong, or you can say right, not right. How many are correct in a multiple choice? Ever. 1. 1 out of, in this case, 4. Therefore, 3 out of 4 are incorrect. 0.25 if you'd like, 0.75 if you'd like. That's your choice. And then your second question would be, again, you could have right, wrong, right, wrong. So let me just fast forward. Are these events dependent or independent? Independent, right? Like the fact that the first one had 1 right answer doesn't change that the second one will also have just 1 right answer out of the 4. Right? It doesn't. So you should see that these are independent events. So both right. Now I need to make a little bit of a. I need to make a choice here. Probability of both right is only this branch here. Probability of right and right is a quarter times a quarter. If you had 3 questions, you would do this 3 times. 10 questions, 10 times, right? So this is 1 over 16, which is 0.0625, which is 6.25%. So this is, I will just go here, probably is 0.0625. You can just look at the page and see where we got that from. Probability of both wrong. It's similar, but you've got more chances of getting things wrong, right? So this is probability of wrong and wrong, which would be 3/4 times 3/4, which is 9 over 16, which is 0.5625. Okay. What about the last one there? When it says at least one correct, what would you do? Ooh, I know. You told us to go 1 minus all wrong. Correct? If it's at least one correct answer you're looking for, you're going to go 100% minus getting them all wrong, which is right here. And quite often, that's how questions will be, where the answer is already, you can use previous answers to help you out, right? Or 43.75% of getting at least one answer right. Okay, hold it. I will scan. I want you to try. I want you to try still homework, page 40 to 43. As well as go with me to page 48. I just need to make one change to make it a little bit more challenging. More challenging. Thank you, Mr. Erickson. Can you change page 48? Make it 5 options. Make it 5 options. So on page 48, and I want you to do this whole page 48 as well. I will scan this one and post it. Thank you, guys.